Good afternoon, class. We are looking at section 5.4, the substitution rule. So we looked at the FTC and now the substitution rule. Here's various basic integration formulas that we have seen, from the constant to the power rule. X to the power minus 1 over 1 over x results in ln x. E to the power of kx is 1 over k e to the power of kx. Sine gives you negative cosine. Cosine gives you sine. And of course, we have a constant in all cases. The FTC, there are two parts. One is the derivative of the integral is the function itself, evaluated at the upper limit, which is the variable. The other one is that if we want to evaluate the definite integral, which is a number. So the integral of f of x dx from a to b, which is a number called a definite integral. And we know capital F prime is lowercase f of x. We evaluate f, capital F, at the upper limit and the lower limit, the difference is the answer. Now we are going to get to the last part, the substitution rule. So I'm going to explain what is a substitution rule. In short, substitution rule is the reverse process of the chain rule. We know how to differentiate this. Using the chain rule, capital F prime of g of x times g prime of x. If I want to differentiate that, capital F prime of g of x times g prime of x. And normally we represent capital F prime with lowercase f. That's why this is replaced with this, in essence. What about this? Now, if we let u represent g of x, that's what's known as the u substitution in essence. And then du is g prime of x dx, because remember, du dx is g prime of x and du is g prime of x dx. So the integral of f of u du is capital F of u plus c, where u is g of x. So here's the theorem. Over any interval for which u equals g of x is continuously differentiable and f is continuous on the range of this function, the following relationship holds. The integral of f of g of x, g prime of x dx, this part is du. Then this is f of u, this whole thing is du. This is capital F of u plus c, where u is g of x. Going to make some sense out of this by looking at a few simple examples. So starting with this one. And I'm going to go over the concept of the substitution rule by looking at this tip. Look for a function u equals g of x anywhere in the integrand, and its derivative du or g prime of x multiplied by dx. Whenever you have polynomial functions, the one which is more complicated is a choice of u, in this case x squared plus 5. If I were to differentiate, then du dx becomes simply 2x. Therefore, du is 2x dx. I'm going to move the 2x next to dx. This way it is clear that this is u cubed and this whole thing is du. And this uses the simple case of a power rule. So 1 over 4 u to the power of 4 and a constant. Now replace the u and you're done. Substitution method. Now, in this case, again, we are dealing with a bunch of polynomials. The more complicated piece is the choice of u. And notice that if you differentiate this piece, you get 3x squared. So note that 3x squared is the derivative of x cubed plus 1. That's what the tip of the previous page told us. Therefore, we are going to move the 3x squared next to dx. So we can clearly see if we choose this one to be u, then du dx is 3x squared and du is 3x squared dx. So we are looking at u to the power of 10 du, and that again uses a simple case of a power rule, 1 over 11 u to the power of 11 plus a constant. U is replaced with x cubed plus 1. That's reversing the substitution, and we are done. Again, in this example, we are dealing with polynomials. The more complicated one, in this case x squared plus 3x plus 5, is a choice of u. The derivative is 2x plus 3. So du is 2x plus 3 times dx. So number 9 is just a multiplier, it's a coefficient. You can keep it inside or outside the integral sign, makes no difference. So let's rewrite it in this fashion. So it becomes clear that we have 9u du, the integral of 9u du. And this one, you know, it's 9 halves u squared plus a constant. Again, we are using the power rule on that. Replacing the u with x squared plus 3x plus 5 will give us the final answer. So in short, when we are dealing with polynomials, the more complicated piece is normally the choice of u. What happens when you have fractional expressions? Granted, this one is also known as rational expression. This is not. But conceptually, they work the same. Number one, you want to simplify if you can. If you're dealing with any fractions, you want to put it in lowest step. And when you cannot, normally the choice of u is the denominator. So if we choose 5 plus e to the power of t as the choice of u, you see that the derivative is e to the power of t, in other words, du dt. So du is e to the power of t dt. So to make sure we have everything that we need, I'm going to put the dt at top. Remember, dt or dx, they can never ever go in the denominator. So remember, this is the same as putting the dt next to it. So what you're looking at is du over u. And as you know, the answer is a natural log. And replace the u with 5 plus e to the power of t, and you're done. As always, if you differentiate the result, it should give you the integrand back without the dt. Also, because this expression 5 plus e to the power of t is always positive, because remember the range for e to the power of t is positive values of y 0 to infinity. If you use parentheses, it's okay. For this one, we let u be the denominator. Again, it can't be simplified. So I'm going to write the derivative of this function up here. So du dx is 2x plus 2, or du is 2x plus 2 times dx, and I can factor the 2 out. Now I'm going to put the dx at top, and the method that I approach this is different than the method that you see in most texts. In most texts, they solve for dx. When that happens, I don't. I look at what I have up here, and I say, you know what? Just the number is missing. And again, if you learn this method, it goes a lot faster. Just the number. So if I throw in this number here, I have du, but I have to undo it with its reciprocal. So you can't just put in number 2. You have to also put in number 1/2 because their product is 1. You can do this whenever you're dealing with a number. This is faster than solving for dx. I will show you what happens if you solve for dx. That works in the same manner with a different example. So what you're looking at is 1/2 the integral of the top is du, the bottom is u, which is the same thing as here. So it's a natural log. But of course, u is different. You plug it in, and that's half of natural log of x squared plus 2x minus 1, an absolute value, plus a constant. And you have to keep the absolute value because this could be positive or negative. What happens? So A and B, I wanted you to see them next to each other. What happens if you have the reciprocal of A? And I want to show you everything side by side so you notice you don't need to use the substitution here. Rather, make up 2 fractions. This is 5 e to the power of negative t. This is 1. And as you know, to integrate this, we divide by negative 1. We get minus 5 e to the power minus t. And 1 gives us t and a constant. There is no need for substitution. And that's the idea that I want to make sure everybody's comfortable with, okay? Very straightforward. So compare and contrast. Fractional format, how we approach it. A fractional format that the denominator has one algebraic piece or one term you can divide by, and there is no need for a substitution method. What if you have an exponential format involved? Normally, choice of u is the exponent. In this case, the exponent is x to the power of 5. If I differentiate that, I get 5x to the power of 4. So du is 5x to the power of 4 dx. Let's move this next to dx. So clearly we have e to the power of u du. And the answer is e to the power of u plus a constant. Replace the u with x to the power of 5. And all you have to do, if you differentiate this, you must get the same answer without the dx. You can check your work. Same thing, we are dealing with an exponential function. So the exponent is a choice of u. Again, the derivative is the same thing, 5x to the power of 4, and du is the same thing, 5x to the power of 4 dx. We are going to move x to the power of 4 next to dx so it becomes clear what we are dealing with. So we have e to the power of u here, but du is not there because number 5 is missing. Well, since it's a number, just throw in number 5. How do you undo it? It's reciprocal, 1/5. So you plug in 5, you plug in 1/5. It doesn't matter inside, this is inside or outside the integration sign, it's the same thing. So you're dealing with 1/5, the integral of e to the power of u du. Again, in many texts, they solve for dx, okay? So 1/5 e to the power of u and a constant, and the u is replaced with x to the power of 5 minus 2, and we are done. As always, if we differentiate this, we should get this one without the dx. We want to integrate this, and as always, if you write this as 3x plus 7 to the power of 1/2, the piece inside the parentheses is a polynomial. That would be the choice of u. You know its derivative is 3, therefore du is 3 dx. Now, this is simple enough. I can show you the method that in most texts they approach, and that is solve for dx. So dx is du by 3. That's not the method that I use. I'll show you the other method in a moment also. So if you go with that, so in this equation, you replace 3x plus 7 with u, so square root of u, and you replace the dx with d over 3. Of course, this is u to the power of 1/2, and you can put the 1/3 outside or inside. The integration sign makes no difference about it. And then you can move on from here. However, this is what I do. I rewrite this in this fashion. Then I go back to my du and I say, oh, number 3 is missing. Big deal. It's a number. I'm going to throw in number 3. How do I undo that? It's reciprocal. So I throw in number 3. I throw in 1/3. And that is identical to what you see here because this is square root of u. And this is basically du. So u to the power of 1/2 or square root of u du, and this 1/3 remains. I find this a tad easier. Your choice. Let's integrate using the power rule. This piece becomes 1 over 1/2 plus 1 u to the power of 1/2 plus 1. And needless to say, 1/3 remains, and we also have a constant. This 1/2 plus 1 is 3/2. This is 2/3. The product of these two numbers is 2 over 9. 2 over 9. And we're going to replace the u with 3x plus 7. We are done. So both ways, solve for dx or just plug in the missing number. Simple enough, really doesn't make that much of a difference in this case, but in some cases it does. All right, again, why am I putting these two next to each other? And I want you to notice one very simple and important concept, and that is anytime ln x is involved, that's the choice of you. Du is 1 over x dx because du dx is ln x, So du is 1 over x dx, and I'm going to write it two different ways because you should be exposed to it. This means the same as this one, 1 over x dx or dx over x. Now, because I want to be clear as to what we have, I'm going to rewrite this in this fashion. I'm going to rewrite it as ln x to the power of 2 and then 1 over x dx. Please understand these two expressions are identical, but now that we wrote it in this fashion, clearly this is u squared, this is du, and that uses the power rule. 1/3 u cubed plus a constant replace the u with ln x, and you're done. Now, one thing I want to make a point of before we move on. Ln x to the third is not the same as ln of x cubed. Those are two different things. This can be simplified to 3 ln x. They are not the same. Make sure you keep this in the parentheses. For part B, we are going to use the same u with du. So I'm going to rewrite this so it becomes clear what we are dealing with. 1 over ln x times dx over x. Over here, I used 1 over x dx. Over here, I'm using dx over x. There is no difference between the two. I just want you to be exposed to both ways of writing them. So this is 1 over u. This is du. And you know this gives you a natural log of u plus a constant. U is replaced with ln x. The answer is ln of ln x. Ln of ln x, everybody. Ln of ln x plus a constant. Again, there's a reason that I have these two questions next to each other because we are dealing with the sinusoidal functions. What happens when the argument has an exponent? Then the argument of sine, namely x squared, is the choice of u. The derivative is 2x, therefore du is 2x dx. Let's move things around. Let's move x next to dx. So it becomes clear in a matter of comparison. Over here, and number 2 is missing. Again, you could solve for dx, but the easy way, number 2 is missing. So if I throw in number 2, then I have to throw in its reciprocal, which is 1/2. Remember, the product of these two must always be 1, and the two must be numbers and nothing else. Now you're dealing with sine of u du. The derivative of sine is cosine, but the integral of sine is negative cosine. So negative 1/2, we have the sine, negative 1/2 cosine u and a constant. So negative 1/2 cosine of x squared plus a constant. And as always, you can differentiate the result and it will give you the answer here without the dx, everybody. Will give you the same answer without the dx. What happens here? Anytime you have sine and cosine, the function that doesn't have the does have the exponent is a choice of u without the exponent. Sine x to the second power, that's the meaning of this. If it helps, you can rewrite this as sine x to the second power. Therefore, u is sine x. And the derivative of sine x is cosine x, therefore du is cosine x dx. So let's rewrite this as the integral of u squared du, and that uses the power rule, 1/3 u cubed plus a constant. So 1/3 sine x to the power of 3, which we can write with sine cubed x plus a constant. Now, again, I wanted you to be exposed to both questions side by side. So think about this. What happens if we are dealing with the integral of cosine to the power of 20 of x sine x dx? Remember, the choice of u is the one that has an exponent. So cosine is being raised to the power of 20. That is the choice of u. The derivative of cosine is negative sine. Therefore, du is negative sine x dx. I want you to finish this at home. And again, see how similar it is to part B. You can easily finish that. Substitution for definite integral. Definite integral of 2x times x squared minus 1 cubed dx as we go from a equals 1 to b equals. There are two methods of handling definite integrals. Remember, with substitution, definite integrals end up being a number. So first and foremost, I'm going to move the 2x next to dx so it becomes clear what I'm dealing with. And as always, if you're dealing with polynomials, the more complicated one, in this case x squared minus 1, is a choice of u. And its derivative is 2x, therefore du is 2x dx. So the first method is to return to the original variable. So u or g of x is x squared minus 1, du is 2x dx. So the first method, you're going to go back to the original variable. So we are going to write this as u cubed du, and we are not going to keep the track of the limits. It doesn't matter because we are going to go back to the original one. Clearly, this is 1/4 u to the power of 4. Again, I'm not going to write the limits. Now I'm going to change the u to x squared minus 1. And when I do that, then I can use the original limits 1 and 2. Original limits 1 and 2, I can use them now. And it's pretty straightforward, everybody. So let's see what happens next. Well, if I plug in the upper limit 2, I get 2 squared 4 minus 1, 3. 3 to the power of 4 is 81. If I plug in 1, I get 0. So I get 81 times 1/4 makes it 81 over 4. And it's absolutely perfect. However, the second method is to keep track of the change and find out the new limits, because over here we didn't write the limits. Those limits 1 and 2 are not the same as the limits for u. So the lower limit x or a equals 1, put this into this function. 1 squared minus 1 gives you 0. So the lower limit was 1 and the new lower limit is 0. The upper limit was 2. Now put it into this. I put the 2 here, 2 squared, 4 minus 1, that's 3. The new lower limit, now we have it. So over here or over here, we have the lower limit. So this one, as well as the upper limit. So it's the same as if we were to rewrite it over here from 0 to 3u cubed, or 1/4 u to the power 4 from 0 to 3. So you can't go with the original limits. Now, if I plug in 3, 3 to the power of 4 gives me 81, 0 gives me 0, so 81 times 1/4, I get to the same answer. Which gives rise to this theorem. If g prime of x is a continuous function on the interval of closed interval of a to b, and f is continuous on the range of u or g of x, then the integral of a to b f of g of x, g prime of x dx is the same as the integral of f of u du from g of a to g of b. In short, it means if you have this one, you can stick with the original limits here. Or this one says, if you have this one, when you change it to this one, change the limits. That's all it says. Change the limits, calculate the new limits, you're in good shape. That's the meaning of this theorem. Let's look at a couple of examples. For example, here we want to evaluate this, and we know it's a definite integral which will give us a number. So we choose 25 minus x squared as a choice of u. We know the derivative is negative 2x dx. The derivative is negative 2x. So du is negative 2x dx. We are going to move the x next to the x. We compare and we see everything is in good shape except minus 2 is missing. Again, you could solve for dx or just follow this number negative 2. Throw in number negative 2. How do you undo that? It's reciprocal, negative 1/2. Again, the product of these two numbers must be 1. So we are looking at the negative 1/2 integral of square root of u du, and I'm not going to write the new limits yet. We will look at it later on. But for now, we are not going to keep track. And so we're going to rewrite this as u to the power of 1/2. This we have seen it before many times. This part gives you 1 over 1/2 plus 1 u to the power of 1/2 plus 1. 1/2 plus 1 is 3/2. So let's do this. This part is 3/2. This is the reciprocal of 3/2 or 2/3. If you multiply 2/3 by negative 1/2, you get negative 1/3. So the answer is negative 1/3 u to the power of 3/2, and we want to evaluate it from the lower limit to upper limit, which we don't have. However, we can go back to the original variable x and go with the original limits 3 and 4. So we can go this route. And that's fine. However, if I want to find the new limits, all I have to do, plug in 3 in here, gives me 25, minus 3 squared, which is 9, gives me 16. The lower limit is 16, the new lower limit. I plug in 4, I get 25, minus 4 squared is 16, and I get 9. So the lower limit is 16, the upper limit is 9. So I'm going to replace them here. And whether you want to use this one or this one makes no difference. I'm going to use this one. It's a tad easier. So I'm going to keep the negative 1/3 out. Again, everything that I'm going to do is just basic math, elementary algebra. So 9 to the power of 3/2 minus 16 to the power of 3/2. This means square root of 9 cubed. This means the square root of 16 cubed. Square root of 9 is 3. 3 cubed makes it 27. Square root of 16 makes it 4. Cube it is 64. 27 minus 64 is minus 37, and minus 1/3. Their product is positive 37/3. Here's another example we want to do, and as always, dealing with polynomials, the one with the more complicated case, in this case 2x cubed minus 8 is a choice of you. Its derivative is 6x squared. Therefore, du is 6x squared dx. Move the x squared next to dx. You see everything is in order except number 6 is missing again. You can either solve for dx or say, okay, number 6 is missing. It's a number. I'm going to plug in number 6. So if I plug in number 6, I have to put its reciprocal in also, which is 1/6. Again, this doesn't matter in or out. It's just what matters is that the product of these two must be 1. Again, I'm not going to write the limits because we are going to calculate the limits. Plug in 0. It gives you minus 8. Plug in 2 gives you 2 times 2 cubed, which is 8. That's 16 minus 8 is 8. So the lower limit is negative 8. The upper limit is positive 8. Okay. And this uses the power rule, 1/4 u to the power of 4. With this 1/6 will give us 1/24. And I can use the new limits, or I can go back to 2x cubed minus 8 instead of u and use the original limits. And I hope you see that this is easier because we are going to rewrite it as follows. 1/24, 8 to the power of 4 minus negative 8 to the power of 4. What you notice is that the exponent is even. So 8 to the power of 4 and negative 8 to the power of 4 are identical. Their difference is 0. The rate of growth of a fish population was modeled by this equation, where t is measured in years since 2000 and g of t in kilograms per year. If the biomass was 40,000 kilograms in the year 2000, what is the predicted biomass for the year 2020 and rounded to a whole number? As far as the rounding class, you rounded at the end, not any of the intermediate steps. So let's explain the situation. First and foremost, we are dealing with a capital G of t that represents the biomass of fish at time t. Then this is the growth rate. That means it's the derivative of this function. So capital G prime of t or lowercase g of t is this. With this being g of 0, it's just 40,000. The initial value. Because we are taking the year 2000 to represent the initial time. So we are dealing with 20 years later. So based on the net change theorem or accumulated change, the amount of increase in the biomass of the fish is the integral of this function, g of t, from 0, the year 2000, to 20, the year 2020. So replace the lowercase g of t. And the only reason I chose this because it is using the substitution method. We have seen this type of question before. And if you recall, anytime we are dealing with a fractional format, after we simplify, the choice is the choice of use the denominator, of course, without the exponent. Now, I want to show you quickly what happens if I differentiate it here. So if I were to differentiate this, okay, I get du dt is 5 e to the power of minus 0.6t times minus 0.6, and that is negative 3 e to the power of minus 0.6t. Therefore, du is the same thing times dt. Now, remember what I told you. What we do, we look at this number. If it's missing, we create it. Now, there are two ways to create this. You can take the 30,000 out and say, okay, I'm going to put a negative 3 in, minus 1/3 out. Or you may notice this is the product of negative 3 and some other number, which happened to be negative 10,000. So you keep the negative 3 in, you put the negative 10,000 out. You do that because the numerator now is simply du. And the bottom is u squared. And I'm not going to write the limits yet. We will look at the limits in a moment. We have done this integration before. We bring this up. As u to the power of minus 2. And we use the power rule, 1 over negative 2 plus 1, u to the power of negative 2 plus 1. And this thing becomes minus u to the power of negative 1. And we write that, and I hope you recognize that minus 10,000 and minus gives you positive 10,000 divided by u. I want to show you the limits. So you put the 0 in here to find the lower limit, 20 in here to find the upper limit. So first and foremost, we are going to use this one. So I'm going to put the 0. When I put the 0, I get the 1 plus 5 e to the power of 0, which makes it 1 times 5 is 5 plus 1 is 6. The lower limit is 6. Now I'm going to put the upper limit. I get 1 plus 5 e to the power of minus 0.6 times the upper limit of 20, which gives me 1 plus 5 e to the power of minus 0.6 and 20. The product is negative 12. Now what happens, class? This number is very close to 0, and the upper limit ultimately becomes really 1. So this is the exact answer, but this is almost 1. So if I write it in this fashion, notice the upper limit is 1 point. Then you have 400,000,000,031. This is almost 1. So that means 10,000. So by the way, I hope you see that this is 10,000 over u. So 10,000, I take it out, 1 over u. So 1 over 1 minus 1 over 6 gives you 5/6, and it gives you this answer. Now, again, I have this. And this was the initial value, 40,000. So I need to add that. So let me clean up the mess. I'm going to add the initial value of 40,000, and this is the final answer. 48,333 kilograms in the year 2020. If you recall, when we did a similar question which didn't need the substitution, here's the second method. I said, you do this and you end up with this answer, right? So this answer plus a constant, here's the second method. This answer, replace the u, here's the second method. And of course, g of 0, we said is 40,000. So replace the t with 0. This whole thing must become 40,000. So 10,000 divided by 1 plus 5, which is 6 plus c, must be 40,000. And that gives us the constant. So replace the constant here with this number. Since we are interested in finding what happens in the year 2020, we're going to replace the t with 20, and that must give you the same answer. The advantage of this, if the question was, okay, predict the biomass for 2020, 2025, 2030, and so forth, all you have to do, go into this formula and replace the t with 20, 25, 30, you name it. That's the advantage of that. I want you to be exposed to these questions again side by side so you can compare and contrast whenever we have a rational expression or a fractional expression. After simplification, the choice of u is 1 plus x squared, the denominator, of course, without the exponent. And as you know, the derivative is 2x, therefore du is 2x dx. So for both of them, we're going to use that. This one is the integral of du over u. The result is a natural log of u plus a constant, and u will be replaced with 1 plus x squared. In this case, if you don't use the absolute value, is fine because 1 plus x squared is a positive value. This one, du over u squared. We have done this before, but let's go over it again. Let's rewrite this as u to the power of -2 and use the power rule on that. We've done this a number of times. So this is 1 over -2 plus 1 u to the power of -2 plus 1 and a constant. As you know, this ends up being -1. 1 over that is -1 u to the power of -1, which is -1 over u. So for this one, -1 over u, which is 1 plus x squared plus a constant. So this ends up being a natural log, but not this one. What about this one? Some of you may see the answer. If you don't, you have to go with the substitution. You let the denominator be the choice of u. Du dx is 1. Du is simply 1 times dx or dx. So what you're dealing with is the integral of du over u. And that, we know the answer is a natural log. U will be replaced with x plus 3. And that's the final answer.